the idea behind this talk is that this is meant for a very broad audience. It's not going to go into any one area in detail of machine learning. Machine learning is a broad area, broad subject, right? So the key idea is this, that we will look at what are the foundations, in the sense that what are the concerns that are machine learnings, right? What does machine learning try to achieve? Right? What are the key concerns and how are they technically addressed? We'll take a look at that. That will give a nice flavor of what actually machine learning folks do, right? And what they are worried about, right? Post that, we'll look at some applications, because machine learning has become very popular, and some of the applications that have come out are very powerful, right? So we'll look at some applications, and I'll take you through two specific applications when we come to that. And post that, we'll go on to like how is machine learning sort of, as a field matures, it forms linkages and connections with other fields, where ideas from other fields come in, and it in turn contributes to other fields. That kind of stuff happens, right? So how is that happening? We'll take a broad overview of that, and then get into two specific examples that had interested me. So that's a rough idea of the talk. Foundations first. So, in order to illustrate what are the key concerns of machine learning, it might be good to take the small area of supervised learning, right? I'll explain what is supervised learning and talk about how that framework is set up. So first of all, broadly machine learning makes you, or the idea is to make machines learn, right? That's very evident from the words machine learning. But then there are several ways in which to make machines learn, right? So supervised learning is one of them. And what we look at is how does supervised learning sort of, in the structure or framework of supervised learning, sort of address the concerns of machine learning. That will give you an idea of what the concerns are and how they are addressed. So the framework basically consists of 4 parts, right? You need to have data in order to learn from data, and you need to have a model, right? The model is just a hypothesis of possible stuff that you can learn from the data. Let me take a simple example here. Suppose this data that I have plotted here, it's 3 kinds of flowers, and their petal length and sepal length. Okay, it's a very popular data set. Now, they are 3 kinds of flowers, you know that, because I have plotted them in different colors for now, right? Now, if a machine learning model were to learn this in a supervised manner, what you could potentially do is that you could say that, hey, I'll label each of these data points, which is actually petal length and sepal length axis. I just skipped the axis here for now. What you could tell the machine or the algorithm is that each of these data points, petal length, sepal length, x, y, it has a label associated with it, right? It's either red flower, green flower, or blue flower, right? Now, that would be the broad statement that, or what you would want the machine to learn. Now, the way you would set it up is this, that you would potentially say, as a simple example, that my machine or my algorithm should learn to divide these into 3 buckets, right? And it divides them according to a straight line. That straight line could be either here or here or here or here. It can move around, right? Now, the fact that it is a straight line division, that places certain restrictions on what kind of boundaries you can have between these classes, right? You can just move them around. You can't make them curve like this. For example, you see here that a straight line will not exactly divide it into blue and green classes, but you cannot do anything better than that, because the hypothesis that you have is that this is a straight line, right? So a model is just a certain set of, it's exactly what a mathematical model is, right? A statistical model. All it says is that there are certain parameters that need to be estimated for example, where the position of the straight line is, right? And it has certain assumptions, the fact that it is a straight line here. Next comes the cost function. That's a way of defining error, right? If I place a straight line here in the middle of the blue thing, it's not actually dividing it into 2 classes, right? So what is the error? And if I define what is the error, I can try to minimize the error using some optimization technique, right? So I minimize the error and move the straight line in such a manner that it minimizes the error. So I define the error here, right? I minimize the error, and that point of minimum error that will define what parameters my model has, where the straight line sits. Okay? So if you think about these 4 constructs, data, model, cost function, and optimization, these are basics, the basic structures on which supervised machine learning is built, right? And the straight line function or the linear function here might get more complicated, the data set might get more complicated, the cost function, how you calculate error, might become more complicated, but the basic structure remains, right? All the complexities come in the ways in which these things are defined. Is that okay so far? Yeah.
So what defines the slope of the straight line?
Yes, it does. It's not defined. So there are two if it's a straight line, there are two parameters to estimate, right? One is the slope and one is the intercept. So this would be it's a linear model or a linear decision boundary between these two, and there are two parameters to be estimated in that while determining the decision boundary here. One is slope and one is intercept. So you can not just, as I said, you can not just move it like this, you can also move it like this. Does that answer your question? And whether it should be like this or like this, that's also something that's estimated by minimizing the cost function. Now, when I say minimize the error, what error are we talking about? So suppose you have a data set, right? And you figure out, you put down your cost function, you say what is your model, what's your hypothesis, and you have a mechanism for reducing the error also, optimizing the cost function also, right? How do you measure the error? On what data do you measure the error? So a machine learning system should learn, right? And learning does not just mean reproducing the data that I showed to you. That's basically memorization, right? Learning involves generalization. So suppose the idea is this. Suppose I have a data set and I train my machine learning model on that. The same process that generated this data set might generate new data. Take a simple example, right? People do credit card transactions, right? And while doing credit card transactions, they a lot of data about the people is collected, where they do the transaction, who they are, and their background information, what transactions they have done previously, etc., etc., etc. Right? Now, the same set of customer group or people are going to generate new data in the future. And if you want to identify fraud in credit card transactions, the model that you trained on your data that you collected should work in the future. Otherwise, it's a useless thing, right? So how do you make sure that the model that you trained on the data set that you collected actually works in the future? The idea is generalizability, right? It should learn characteristics of the thing that produces the data. That's the only way out, right? It should learn characteristics of that so that it can understand that the new data it generates, that whatever the source generates, would be of so and so fashion, and therefore I can make predictions of so and so fashion on that, right? Therefore, when you want to test your model, or so what does testing a model mean, right? You want to minimize error, basically, and say that this is a good model or bad model. That's basically what it means to test a model, right? So when you say whether this is a good model or a bad model, the error that you should be looking at is not really the error on the data on which it was trained. It's the error in the new data that's going to come up, right? But you don't have that data, so what do you do? Right? So there are several ways around for this. One of them is called cross-validation. Okay, we'll come to the pictures, but before that, so what you basically do is that you divide your data sets into a training set and a test set. You train on the train set, and the test set the model has never seen before. You actually test your model on that. That's the idea behind cross-validation, right? Now, coming to generalization, there is one other thing that I wanted to mention, right? There is this issue called overfitting, right? So your hypothesis class of your model can be various things. It can be a straight line, it can be a complicated curve, whatever, right? Now, if the hypothesis class is complicated enough, say it's a very higher order polynomial, it can actually learn to fit the data exactly as it is, right? This part, the open circles, not the closed circles, or not the filled circles, that is the training data, suppose. But suppose it does learn that, what will happen is that when new data comes in, which are the blue dots here, the errors will be large. And the reason for that being that the system behavior that actually produced the data the real ground truth is actually the dashed line, right? So dashed line is there, which is the ground truth. There are errors generated when the data is captured or when the data is produced. Those errors cause the points to lie around it, but your model actually learned to fit the red curve on the training data, which is the open circle. Right? Now, what it's doing is that it's exactly trying to match the training data. It's actually sort of memorizing the training data. So if such memorization does happen, your test error will be large. Error on the test set, which is the blue dot, will be large. Whereas if it had actually figured out that this is the dashed line is the approximate curve to be fit, then the error would have been smaller, right? So this idea of generalizability, that's exactly what I'm talking about. Even if you fit the exact dots here, the open circles here, that does not mean that your training error might be very small because it's exactly fitting. It's in fact 0, right? Training error. But your test error can become quite large. So while training a model, one of the ways in which this appears is that as you keep on training, you see that your training set error keeps on decreasing. Whereas your test error comes to a minimum and then start increasing, which is when you know that your model is starting to overfit or starting to memorize the training data and becomes less and less generalizable. Right? You ought to stop your training here. Now, coming back to cross-validation, which I mentioned earlier, about testing it on a test set, one of the ways in which, nice ways in which to do that is actually to divide your entire data into 5 parts, say, right? And what you do is that you train on the first 4 parts, test on the 5th part, first iteration. Next, you train on the 1, 2, 3, and 5 parts, and test on the 4th part, in the next iteration, calculate the error. And the net error that you report is, oops, this should be in red, all right? That's a mistake. The net error that you report is the average of the errors in each of these iterations, right? So that tells you, so there are 2 things that are happening here. You are doing training and testing on separate sets. So you are testing for model generalizability. Secondly, you are using the entire data to train, whatever data you have. So even part 5, which was not initially used, is now being used to train the model, right? So this is called k-fold cross-validation because you are dividing or folding the data into 5 folds or k-folds. Yeah. Now, you can build your model and you can, if you take any machine learning textbook, there are like 30, 40, 50, 60, whatever. Huge number of models that you'll find, right? And the question is, what sort of model should you use? Right? An important thing there that everybody has their own favorite model and people have their own flowcharts about what model you should use for what, etc., etc., etc. Right? So broad classification, you can say. For classification, there are certain models. There are other machine learning tasks like clustering for which there are other models. So the supervised learning thing that I talked about, which we discussed until now, it's typically used for 2 kinds of things. Either to classify as this flower or that flower, which is the first example we saw, right? Or, like in the previous example, it can be used to fit a curve. This is called a regression problem, right? Regression can be thought of as classification when the classes become too close to each other, lies on the real line, right? So classification and regression are typically treated in a very similar manner. So everybody has their favorite model, but the important thing to understand is this, that there is actually a theorem in machine learning foundations literature. It's called the no free lunch theorem, right? It says that if you have an algorithm or a model that performs fantastically on a particular data set and on a particular problem, it will not perform fantastically on the others, right? So it is not just the model that tells you how much error you have, it's also the data and the problem. Right? So you cannot have a mega model that comes and solves everything. This is a nice thing, otherwise, I mean, what's the fun, right?
What's the assumption that goes into this?
Into what?
Surely you could have, if you made sufficiently complicated models, you would be able to. So what's the precise statement of this? No, if it's a theorem, there's no freelance.
Yes. See, the precise statement, I'm trying to recollect here, would be this, that a highly specialized algorithm Give me a minute. Yeah, I think it comes around to this, right? So given a class of algorithms, and if you're looking at their performance, right, it says that no algorithm can beat the other algorithm on all tasks, given that class of tasks that you have. So you have given a class of algorithms or models, and you're given a class of tasks, right? And what it says, the mathematical definition I'll have to go and look up, but what it essentially says is that you cannot find a single model that beats the other model on all these tasks.
But beats meaning asymptotically beats in terms of complexity? Or?
No, it beats in terms of error, right? Lower error. So the key thing you are trying to achieve here is lower error, that's it.
Is there a constraint on how much time you're allowed, or how many resources you're allowed to have? Or?
See, in real world considerations, time and resources are both fixed, right?
Okay, but how about one algorithm which says, if classification, then adopt one of the top right? If you always given a bunch of algorithms, you can always construct a meta algorithm that combines all of them.
See, no, your tasks are also different, right? Your task could be a classification task, it could be a regression task, it could be see, each of these buckets here are actually kind of task groups, right? Within this task group, you can have several different algorithms, right? So you can have tree-based algorithms, you can have SVM-based algorithms, right? Kernel-based algorithms, so on and so forth, or neural networks or whatever. Now, given a specific kind of a task and a set of problem tasks within that, the statement is that you cannot find an algorithm that is good at all these tasks. Okay.
Yeah, no.
Yeah, asymptotic behavior, I mean, we'll have to look up. I don't know what the statement of the no free lunch on that is.
Yeah,
but
it's like a very powerful theorem, some surprise, because it's
yes.
Some surprise about what the statement is, because it sounds like a very general theorem in which. What are the assumptions that go into?
Yeah, I understand.
Our brains, for example, do a lot of tasks.
Yes, I understand. See, I'm never bothered about that because typically when we actually take up a machine learning problem, right, your time limit, you never get into asymptotics. Your data set is constrained, your whatever fixed, your time limit is fixed, right? And your computing power is fixed. And within that constraint, I mean, all you need to know is that, I mean, hey, this particular model gave me fantastic result there. That's not going to work here. I need to figure out what data it is, what problem it is, and then try to figure out what assumptions the model need to have. Right?
So, would the machine actually decide which of the task by itself? Construct an algorithm which first decides which kind of task you want to address.
No, I mean, I don't think so. No. See, coming back to the way this problem is set up, right? You need to specify the problem. Only when you specify what kind of a problem it is, can you build these constructs.
No, but if you actually showed a broad characterization of the kind of task.
Yes, yes.
So can the machine actually try to determine what kind of problem?
It is either it is too trivial or too complicated. I'll give you a trivial example, right? If the thing that you want to predict or learn is a number, say, take fraud for example. Is that person going to commit fraud or not? That's a class of fraud or not. I mean, you can of course write a small program that figures out based on the outcome variable, which is fraud or not, is it a discrete variable or a continuous variable? So you can figure out whether it's a classification task or a regression task. But that's like a no-brainer, right? If you get into a more sophisticated situation where you want to sort of make your I wouldn't even say model, you want to make that whatever machine learning thing, figure out what the situation and respond to that, that's a very tough call. I don't think, I've never heard of anything like that.
I have a question.
Yeah.
You said here that you define the task and it learns and like you define what's the line here, like how to distinguish red and blue.
What red and blue? Okay, yeah.
But like how did Alpha Zero learn play chess on its own? There you don't define. I mean,
your task is very well defined there, right? I mean, you need to beat everybody at Go. That's your task. And your training set, data set is also well defined. It is basically all the Go games that have been played, right? And your cost function, which coming back to this, is very well defined, right? You need to beat everybody.
We don't know how to do that now. I mean, here we define that this is red, this is blue. We know, but we just said everybody.
Agreed. But still your task is defined. It's not label data set. So I'm saying that here, it's red and blue and green. That's called label, right? Each data point has a label, red, green or blue, right? In supervised learning, which typically comprises of classification and regression, right? You have to provide a label, and then the algorithm sort of learns to figure out the label by itself. That's the learning task there, right? In AlphaGo, it's a very different task that you're providing it. So AlphaGo uses something called reinforcement learning, right? Or
4 hours.
Huh?
4 hours.
Okay, maybe, but what I'm saying is that it's a different kind of learning task that it has, right? Its learning task is how do I, so reinforcement learning is something very different from this setup, all right? This construct or this framework is useful for supervised learning, and it gives you an idea of what the key concerns are. That's why I started out with this, right?
It's not original, it just does work.
What?
You mean, just the task is defined, you just know you can predict the outcome to a certain extent. That's what you mean by
no,
supervised learning.
No, it's not. So let me give you a good example of supervised learning, right? Let's take the fraud example, for example. It's very difficult to actually build a system that can recognize fraud. Okay? Now, the reason is that you have a data set on which you are training the machine learning model. That's fantastic. But you don't know what the user is going to do next in order to do fraud. And people are getting more and more, inventive at doing fraud, right? So you don't know what is going to come next. A good machine learning model can sort of figure out from the data the patterns that the user might exhibit while committing fraud. That's the generalization that it's doing, right? So it's not trivial. That generalization is not trivial. Is that okay? Answer?
Both are original in their own ways, reinventive and...
Yes. Any questions? I mean, maybe I'm like glossing over a lot of things here. So if you have any questions, please bring it up. Yeah?
The way we label data, so if there's some data after some point, we can decide to assign some new kind of new parameters for the same. So we can say red flower, a colored flower, and we can assign a number of petals and things like that.
Yes.
And then we also have to change the model.
Yeah. So as you're typically, right, the way a model is written, or at least in the framework of supervised learning, is that you have several different things what are called predictors, right? And you have one thing called target or outcome, right? Here the target or outcome is the class of the flower, red, green or blue. The predictors could be, in this particular data set, the predictors could be length of the petal, width of the petal, length of the sepal, width of the sepal. That's the data that I have plotted here, right? Like I have plotted 2 dimensions among those 4. Okay? If you add other dimensions, like for example, does it grow in this region or that region? Or does it, how tall does a plant grow? Learning from that new data, which is larger now by those 2 or 3 additional variables, that might require a new model. It might not be the same.
But it can have impact on clustering. For example, in physics astronomy, people use, are these galaxies same kind of galaxies or not? They cluster them using machine learning.
Clustering is
then you have the new variable, then clustering will change depending on that.
Clustering is, so this framework does not apply to clustering. Clustering is an unsupervised learning technique. Okay, so clustering does not, you don't give label data to clustering, right? Clustering tries to, by its own, figure out, like, are there regions of space where data is clustered together? That's what clustering does. And that space can be, that distance in that space can be defined in various forms, right? You can have Euclidean distance, you can have distance, other similarity measures that make up the distance.
I think also that depends on what descriptors are you using, the better ones, which are more significant and not more interesting.
Yes. Yes. So, yeah, what predictors you use, some of them might actually have predictive power, some of them might not, right? So, the whole process of model fitting, at least within this framework, actually is a very, very iterative process, right? You start out with some hypothesis. So, it's very much like doing physics, like you said, in the sense that you start out with some hypothesis about the source that is generating this data, and you try to collect some data that might actually tell you, be able to help the machine learn what class of flower it is, right? Then you see whether that that hypothesis was initially correct, right? Whatever you thought, how the data is generated, whether that was correct by actually fitting a model and calculating the error. If you find that the error is large, you go back and see, hey, what other thing could this source behavior be that is actually generating the data? Then you collect other variables probably, right? Yep. Another thing that is of interest while building such machine learning models is what is called the curse of dimensionality, typically, right? The key idea here is that, like we just discussed just before this, what the classifier is doing is identifying regions. If you go back to the first picture, I'm not going back again, I've been going back and forth, but if you go back to the first picture, what it's doing is identifying regions and saying that in this region, the values corresponding to this region belong to this particular class. It's learning to identify that, right? Now, as the number of dimensions becomes really large, say 100 dimensional or 200, there are situations where you have 1000 variables, right? Those instances come in genomics, for example, right? When you have so many variables, the actual value of plotting or looking at data in those high dimensional space becomes irrelevant, because data becomes sparser as the number of dimensions you have increases, right? And it becomes very difficult to actually identify regions that have a significant concentration of a particular kind of class. Okay? That's called the curse of dimensionality. When you have that, what do you do, right? You can't do anything. You will fit a bad model, basically. There are some things you can do though, which is what we come to, is dimensionality reduction. Right? What you could potentially try to do is look at, in this high dimensional space, the data is distributed in some manner. What are the directions or eigen directions along which the data is spread the most, right? And I will look at the data along those eigen directions, right? So that's typically accomplished by this thing called principal component analysis, right? You identify directions along which, so this is the, if you take this data, right? Suppose it's distributed in this plane, within this area, right? It's two-dimensional. What you say is that the first principal component is along this direction, second principal component is along this direction. So it basically identifies eigen directions along which the data can be split up or spread out, right? And says that if you have a 100-dimensional space, you can say that, hey, I look at the first 10 dimensions because that is where the most of the spread of my data happens. That's where most of my data lies, right? And you reduce the dimensions and then try to solve the problem in those 10-dimensional space. You are incurring some error, but then your models work much better in this lower dimensional space. So you could probably get better results rather than working in that 100-dimensional space, right? Even with that error that you're incurring. Typically, right, any data, take 3 dimensions, right, 3 dimensions. And you have you remember the first picture, right, first slide? There was the red cluster here. Imagine that in 3 dimensions now, right? Now, in those 3 dimensions, it's distributed in some particular manner. That thing, that distribution, needn't be symmetric, spherically symmetric. It can be stretched along one direction, slightly stretched along another direction, right? All this is trying to identify is what are those directions along which the maximum stretches are there for the data. The variance of the data is maximized along those directions. Okay. Now, there is a related thing which you can do, when your data has this property, that it actually lies on a submanifold of the high dimensional space you're looking at, right? What you do then is that you try to identify what that submanifold is, and that's called manifold learning, right? That's also a way of dimensionality reduction, typically non-linear, because your manifold is not going to be a plane in 3D, right? So that process of dimensionality reduction is very useful, and I'll just give you 2 examples here. So one of the sort of classic machine learning data sets is the data set of handwritten digits. Anybody who's sort of looked at machine learning might have come across that. So you have numbers, I think it's 0 to 9 or 1 to 10. I think it's 0 to 9.
0 to 9.
0 to 9, yeah. And they are represented as images, right? So it's typically given as 28 cross 28 pixel images. or 32 cross 32 or whatever. So the image looks like this typically. It's so one that is written here will have sort of ones in this area and zeros everywhere else, kind of. Sorry about that. I'll just silence this. So it's actually very high dimensional data if you think about it, right? Because even if each of these is sort of pixels is binary, it's black and white image, suppose, right? It is actually 28 cross 28 dimensional data, right? Along each direction you can have two values. It's high dimensional data, right? But then the number 1 or any number that you want to write 0 to 9 actually occupies only certain dimensions here. So it lies in a sub-manifold or in a reduced number of dimensions within that high dimensional data, right? Now, if you can identify what those low dimensional manifolds are, maybe if you look in that space, maybe you can separate out the numbers, right? So if you want to imagine this task that you want to build a classifier that identifies handwritten digits, right? So I write 1, it identifies it as 1. I write 2, it identifies it as 2. And when I write it, I'm always writing it in this manner within a 28 cross 28 pixel thing, okay, for simplicity. Now,
like the number is blank of matrix.
So don't think of this as a matrix, even though I've represented it as a matrix.
It can be a general array, but array.
It needn't, yeah, it needn't even be an, okay, fine, you can call it a high dimensional array. You can just have a vector, right, if you want. Like I wrote it as 28 cross 28 because that is, because 1 is written in 2 dimensions, but I could just as well write these numbers as a single line, as a vector, right? It really doesn't, yeah. So, what is that? What I have done here is try to reduce, so there are mechanisms to reduce the number of dimensions, right? There are models that actually allow you to do that. One such model is made up of neural networks and it's called an autoencoder. Okay, if towards the end, if you have time, we can discuss that in some depth, but think of it as a model, right? What I have done here is reduce the plotted, so digits 0 to 4 here, reduced it to 3-dimensional space and plotted it. And what do you see here? That they are separated out. So if I were to build a classifier to now learn, hey, which is 1, which is 2, which is 3, which is 4, which is 5, the classifier will probably create decision boundaries like this, like this. Does that make sense? Any questions? Right? The question, so just coming back to what we were talking about, we were saying that in high dimensional spaces, it may be difficult to actually create your decision boundaries and separate out classes, right? Or do machine learning the typical way, right? Supervised machine learning. And what we said is that if you reduce the number of dimensions, probably in that low dimensional space, your machine learning model might work better. Now, what we have done here, this is just done using Mathematica. You can build your neural networks in Mathematica, right? You can build an autoencoder, which is a kind of neural network, reduce the number of dimensions here to 3-dimensional space. What an autoencoder does is this, right? It tries to reduce the number of dimensions, at the same time, make sure that when you reconstruct the original data from this reduced number of dimensions, it is reconstructed without much error, right? Tries to reduce the reconstruction error, reduce the number of dimensions in such a manner that if you were to reconstruct the original data from the reduced number of dimensions, that's possible without much error, right? It tries to reduce that error. That's what an autoencoder does, right? Now, basically what it says is that it's trying to retain the information about what it makes 1 a 1 or 2 a 2, while at the same time reducing the number of dimensions. Folks following, or yeah? Just stop me and ask if it's anything.
So this is a countable set, right? The number of possible 28 cross 28.
Yes.
Because it is binary, so you just put 0 1. Okay, so in principle, you can very easily represent the 0 in 1 dimension. There's something else. So I'm a little confused about the dimensional
So what I mean by dimension is this here. You'll probably use a board here, right? So each of the, think of it as a vector, right? So 28 cross 28 is the size of your vector. Each of them can take 0 or 1 values, right? This is a dimension, right? It's not a real line, it's a binary valued dimension.
That's right. It's a
right?
count, yeah. It's a finite number of
States.
But the whole thing I can represent in terms of one number between 0 to 2 to the 28 cross 28.
Yes, you're right. Yes, you're right. Yes, you're right. Yes, yes, you're right.
So now can you explain, so that's, in principle, that looks like a one-dimensional reduction onto a system.
Yes.
This is doing something else, right?
Yes, this is doing something else.
What is it doing?
Now, see, these are not, this is not a machine typed 1, right? So there is no unique, this is a handwritten one. And the way I write 1 may be different from the way you write. So there is no one unique way, or according to the map that you are suggesting, there is no one unique number to which the number 1 will be mapped. There can be many, right? That's one way of reducing the number of dimensions, right? Or I mean, that's one way of representing your, whatever, your data. What this is doing is very different. So I might need to get into some amount of what the autoencoder does.
Just 1 second, so that's a bad way of reducing it, you said. I could try and cluster all the numbers from 0 to the 28 plus 28 into 10 bins. Like, you know, one set of numbers represents 0, 1, 2. And are you saying that's very inefficient? That won't work.
No, I'm not saying it is inefficient. It is only efficient if, so this is say number 1, right? Or all the data points that correspond to number 1, all samples of number 1, that they fall into a set of numbers according to the map you're suggesting, right? Number 2, similarly, falls into a set of real numbers that, or integers or whatever that you're suggesting. If there is a high overlap between these, my classifier will not be able to distinguish.
Oh, there's no overlap, right? The overlap is 0 because one is, I supervised it. I said this is 1 and this is 2. So in the end, the classifier will find a non-overlapping sense between.
Oh no, so
one pixel pattern corresponds to 1, another pixel pattern corresponds to 2. And I'll find some decision which is a non-overlapping.
Think of it this way. I write 1 this way. Somebody else writes 1 this way.
Correct.
Right? The pixels that are on here are different from the pixels that are on here.
Both of them fall in this set of the left.
Sure. Right?
That's
now, imagine that's a real line. Right? And the set corresponding to 1 is here, the set corresponding to 2 is here, suppose.
Right. So maybe what you mean is that you know, because it's a discrete set, maybe that this that distance in this space is not the same as distance in real space, as distance in the integer space.
It's not about distance. The whole point of a classifier is that it should learn to identify decision boundaries that separate the 1s and the 2s in the reduced dimensional space, right? If that is possible, like this, then your mapping is good. If that's not possible, then your mapping is not good, right? It has to identify a mapping in which the classes are separable. The keyword is here, separable in that space, right? So that's what we are trying to do. Now, when you do that, so what an autoencoder does, which we used here, is to map it down in such a manner that the essential information is retained. How does it check whether the essential information is retained? By reconstructing it and saying that it actually does it match what I gave as input. That's why it's an autoencoder. It encodes it and then decodes it and sees whether the decoded stuff is back same as the input, or tries to minimize that error. Okay. Now, while doing that, we also found that the classes got separated. Now, if you want to actually build a classifier saying that, hey, I want to identify 1s versus 2s, I can build it in this space maybe, or maybe a 4-dimensional space where they might be slightly more separated maybe, and that would identify regions as separate. It would be able to construct the decision boundaries.
Reducing it to 1 dimension. Then there's some problem.
There's no problem, but think of it this way. You have data like this, right? And you have data points here, and you have data points here, right? If you project it to this area, you'll get something like this. If you project it here, you'll get something like this, right? So it also depends on how you reduce the dimensionality, right? So certain dimensionality reduction techniques actually make the data separable, certain do not. Clear?
So you're saying that the dimension is a bit higher, where there's a greater chance that these
points you won't overlap.
Yes, that's higher because, yeah, that's correct. Because now if I were looking at it in 2 dimensions, my decision boundary could be this potentially, right? But the problem is if when I make the dimensions too large, everything gets far away and I won't be able to clearly define decision boundaries. So there is a in-between state that you need to get to.
So how do you determine how many dimensions to reduce to?
You try out. You try out. So, I mean, I reduced to 3 dimensions here because, I mean, it's easy to visualize. If it's 4 dimensions, I'll have trouble visualizing, right? I wanted to see what the points look like, whether they look separated. I can only maximum do that in 3, that's why I did 3. I could even do 2. If you just look for MNIST dimensionality reduction on Google, you'll find a lot of instances where using not just autoencoder, other techniques also, right? Where they have plotted these digits in 2 dimensions and they form, separated clusters, right? So you will find stuff like this. Here's are all the 1s, here's are all the 2s, here's are all the 3s. There are techniques that can do that this time. That was just a brief thing to give you some sort of high-level overview of what does machine learning try to do, first thing, how does it try to do that, right, and what are the issues that it faces. Now, these sort of explain within the context of supervised machine learning, right, but these issues like high dimensions or other stuff, error kind of stuff that we saw, they also are sort of pertinent issues in other machine learning problems other than classification or regression, right? What are some of the other kinds of problem machine learning tries to solve? One of them is clustering, right? So if you remember the first red, green, blue data set, and you did not know the labels, suppose, right? You just knew petal length, sepal length, and you wanted to identify, hey, are these actually different kind of flowers? You could potentially do that by, say, using the technique of clustering. You could say that this region seems to contain a cluster, right? And that's separated from the other cluster that is there, right? So the 2 things, points clustering together and that cluster being separated from other clusters, right? So your clustering effectiveness is measured using these 2 metrics. So within cluster similarity and between cluster dissimilarity, right? Those are the 2 metrics that you can use to measure your clustering effectiveness. And you could potentially identify that probably this cluster that I see down here is actually a different kind of flower because this data is different from that data and the processes that generated that data, the process here is which flower it is basically, right? The process that generated that data could be different, right? And then you go and figure out in the real field that, hey, it's different. So clustering can be used to identify patterns that are not exhibited, so patterns that you don't know about, right? You don't have a label there, but you infer that label by looking at the data. There are problems like ranking. There is a whole area called learning to rank, right? So people have given various ranks, suppose, right, for your movie recommendations on IMDb, suppose. And you want to train a model to actually learn to rank. That's a whole area of machine learning called learning to rank, right? Based on what people have done, based on given examples. Recommender systems is another area. The classic example is Netflix or Amazon recommendations, right? Based on your purchase history or what people similar to you have bought, right? It can figure out what you would potentially like. How does it do that? Basically, the idea is very simple. 2 things. It looks at user-user similarity or product-product similarity, right? Recommendations is typically when you want to recommend something to somebody. That's a problem statement itself. User-user similarity means that, hey, I buy these things, you buy these things. How similar are our purchase patterns? Based on that, I'll calculate a distance between the users, right? And most similar users, so suppose me and you are a similar user, right? I have bought some things that you might have bought, but you haven't, right? I could recommend those things to you. That's user-user similarity based recommendations, right? Product-product similarity based recommendations is this, that, yeah, I bought some set of product which is very similar to another set of product, right? Or that they are bought together typically. So how does Amazon do the recommendation? These products are typically bought together. You must have seen that in the Amazon list, right? That's product-product similarity. word embeddings and topic modelings brings us to the area of natural language processing, right? Or text mining. So word embeddings are an interesting way of looking at words in context. Yeah, I'll just quickly walk you through this. We don't have time to get into the detail of all this, but I'll give you an idea overview. So you might have asked the question, right? What are the kind of words that occur in similar contexts? For example, the word, like the classic example discussed is king and queen, right? The word king occurs in certain contexts like palace, kingdom, etc., etc., etc. The word queen occurs in certain contexts like, again, palace, ruling, kingdom, whatever it is, right? Now, can we identify relations between words that occur in similar contexts, right? And can we identify rules based on that? So word embeddings actually allow us to identify rules like a king is to a queen as a man is to a woman, right? So it will identify relationship that exists in similar contexts. And that's again a dimensionality reduction technique that's used there. You project the space of words into a smaller number of dimensional space and try to look at what comes together in that space, just like we did for autoencoders. Topic models are another interesting application of machine learning where you try to identify, given a large number of text documents, what are people talking about there, right? So the classic example in the paper that discussed topic modeling was looking at research papers. And they looked at, I think, I don't remember which area they looked at, but they looked at a set of research papers and identified what are the topics that are being discussed in those research papers, right? In an automated manner. And they went through like tens of thousands of research papers. It would have taken a huge amount of human effort to actually identify that. But they could do that using an algorithm, right? Next part.
Sir, I have a question.
Yeah.
Suppose you want to build an app which recognizes your handwriting. Let's say a very complicated like mixture of equations and English or something like that. Then in which sector does that problem fall?
It recognizes your handwriting, you're saying.
Yeah.
And so when you say recognize, what does recognize mean?
Like drawings. And if you want to make a man-made drawing to a digital drawing, then how do you make?
So yeah, let's break down that problem, right? I make like on Google, suppose, or Google Slides where I'm presenting, I hand draw something, or take one of your Samsung tablets or whatever, right? You hand draw something, and it automatically, you draw a circle roughly, it automatically makes it a circle, right? You draw a rectangle roughly, it automatically makes that a rectangle. That's the kind of stuff you're talking about, right? So that's a classification problem because it's trying to figure out what you just drew with one stroke of your pen, what pre-existing label here being circle, rectangle, triangle, what pre-existing label does that correspond to? That's a classification problem. If you write A, it converts that to A. That's actually, again, a classification problem, right? So it has a predefined set of labels, A, B, C, D, E, F, G, H until Z, and it tries to assign everything that you write into one of those labels.
In
10 minutes. We'll rush. Okay? So, sort of applications of machine learning and its successes, right? You must have heard a lot of stuff, right? Netflix uses machine learning. They give a huge prize for building the best recommendation engine. Amazon uses, Google Home, everything, right? I'll give you two examples which are close to my heart, sort of. I like the examples, right? Oops. Let me just click on that. This is music generated by a neural network. Let me play that. Being projected. Sort of not bad, right? For a machine generated music. Right? So that's an area where we can see a lot of interesting things happening, right? So neural networks, which are one of the most powerful machine learning algorithms we have today.
What input was this thing given? Did you teach it, you know?
Oh, the input given was basically music created by Western classical musicians or piano artists in the past.
But then why is it so hard to come up with something which sounds, I mean,
so this is an example, right? Yes. Yeah, I mean, you can randomly concoct it and come up with something, but people have done it to a more sophisticated level, right? They have done it to a level where they have been, the neural network has been fed music by Bach, and it produces something that's reminiscent of Bach. I'll give you another example. Have you looked at this thing called, app called Prisma? Yes? I'll just write it down. It's a very nice app. I mean, you can download it for free and start using it, right? So that has many styles. So you take a photo, suppose. I take a photo of this room. And then I say that I want to put it in the style of some painter, say, name a painter. Van Gogh, right? I want to put it in the style of Van Gogh, right? It converts that into a style of Van Gogh, right? And it's very, pretty good the way it does it, right? That's because it has learned the style of Van Gogh. Check it out, the app is Prisma. And that's an area called transfer learning, right? You learn from something and apply it to something else, right? Similarly, in music, what people have done is that they made neural networks learn the style of a particular musician, and it can produce music of that kind.
What I'm missing is just imitativeness. And there's originality.
Yes.
So this is the question. What I'm missing is it seems very easy for a machine to imitate. You know, I could imitate, yes. I could cut and paste and make something. Yes. But obviously, what you're saying is algorithm is doing something more, and I'm missing more.
It is generalizing. The key to machine learning is not imitating, it's generalizing. Learn from something and try to understand the original thing that generated it. Learn to understand how Bach would have generated it. That is what even the supervised learning thing that we talked about, that is the key. Okay. And our whole thing of, why should I not train test my data on my algorithm on the training set? Because I want to see how good it generalizes on a new data that it comes across, right? So a good machine learning algorithm can learn to generalize, that's the whole point. The second example is something that we did in my office, okay, for fun. Actually, it's a very useful thing also. Check it out. So this is running on an Amazon instance. It's called a convolutional neural network, and take a minute or two to load because the app is loading, right? So there are many like this now. There are actually startups that have been launched to actually detect diabetic retinopathy, which is a disease of the retina, using neural networks. So what is diabetic retinopathy? If this is what somebody with good vision sees, this is what somebody with diabetic retinopathy sees, right? And it's a problem with the retina. And the way it's typically identified is that there are these special cameras that you can use they're called fundus cameras. You can use them to take an image of the retina, right? You keep your eye closed and it takes an image of the retina. Now, using that retinal image, doctors look at that, right, and diagnose it as saying, hey, you have diabetic retinopathy or not. What we did is train the convolutional neural network, which is a kind of neural network really good at image recognition. So you might have seen that Facebook identifies your photo, right? This is your friend, you are there in this photo and it notifies you. It uses convolutional neural networks, okay? So we built convolutional neural networks that can actually look at a image of a retina and classify it as having diabetic retinopathy or not. Right? I'll show you an example. So we train the neural network and I'm loading test images. So I'm not testing it on a training set, I'm testing it on a test set. Now, okay, I have 5 images without disease and 5 images with disease. Right? These are labels that I already know of the test set. So I can test how good my algorithm is. Right? Let's say predict. Got one wrong with disease. Somebody who had a disease out of these 10 was not recognized as having the disease. Right? This is actually happening. The prediction is happening as I'm talking. Right? So I click predict, but I can load another 10 and predict, and load another 10 and predict. Right? That's exactly what a machine that is going to replace a doctor on some day would want to do. should look at the image, identify whether I have a disease or not, and say, hey, it seems like you have a disease, go to the doctor, right? And this is doing a fairly good job, right? We got around 98 to 99% both precision and recall. Precision and recall measure your false positive, false negative kind of thing, okay?
What about the other two?
What is it?
Why it failed?
Generalization error, 2% or 1%. Cool, I can load another 10 new ones and say predict again. It's predicting now. Okay? So that's the second example that I wanted to show, that machine learning is actually helping us solve problems in everyday life, not just buy books from Amazon, right?
Is it deterministic, like will it make the same mistakes every time, or if you run it with slightly different training sets and things?
No, on the same new data set, if it classifies something as wrong, with the same one trained model, you classify again as wrong. If you want to not classify that as wrong, you need to retrain the model.
I thought the machine was learning with the test data that
No, it's not learning with the test data. So if you want to learn from the test data, you bring the test data as part of your training data. In the next iteration, train the model using that data also, then it will learn.
if you do that, then the result may change with
Yes, yes. So that's why when I clicked it twice, it gave the same error, right, on the same thing, yeah. So these are the two examples that I wanted to walk you through, just to say that it's actually having a lot of impact in our everyday life, right? Listening to new music, nice.
And what about the size of the training set? I mean, for these algorithms,
Yes.
how do they depend on the size of the training set?
The data size actually depends on, remember the first slide. You have a model, and the model has parameters and assumptions, right? The assumption in that model that we looked at was that it's a straight line. The parameters were slope and intercept, right? Neural network models similarly have millions of parameters to learn, okay? Because the size of the data that we are providing in, the data that we used was 512 cross 512, which is itself large. And then there are like several layers of neural networks that go into it, right? Each of which has weights. So neural networks are connected, neurons connected by weights, simply putting, right? Let's not get into detail about that. There are actually millions of parameters to be learned. If there are such millions of parameters to be learned, then you want your training set also to be large enough to be able to learn all this.
So give an order of magnitude.
So we used around 26,000 images, including both the positive class and negative class.
When you say generalization error, you meant the machine or the programmer? I mean, the guy who made the boundaries.
No. So the only error we are talking about is the model's error, not programming error. The model is generalizing, right? Error in that, that's what you're talking about. Some practical concerns that we need to keep in mind while building such applications, right? There are two kinds of things that we need to keep in mind. Anupam, I might need 5 minutes more. Is that okay? How much time do I have now? 5 minutes.
5 minutes.
Fine, we'll see. So, there are two kinds of considerations typically, right? One is the number of decisions to be taken, right? So, take Amazon recommendation for example. Yeah, Amazon Reco Engine. I mean, every millisecond is churning out recommendations to everybody across the world, right? So, the number of decisions it's taking is huge. But what is the cost of a wrong decision? If it recommends a wrong book to me, I'm not going to get insulted, right? Cost of a wrong decision is almost nil. There are other applications where cost of a wrong decision can be very large, right? I'm giving investment advice, I'm Goldman Sachs, I'm giving investment advice to a client who's like investing millions. And if I make a wrong decision, that person is not going to come to me again, right? But number of decisions to be taken there is one, right? So depending on this trade-off, you need to figure out what kind of a system you want, right? There comes in the idea of a human-in-the-loop system, right? So here I'm getting into when you build machine learning or apply machine learning, what are some of practical concerns to keep in mind, right? Human-in-the-loop systems means that you do not make a recommendation directly to the end user, you make a recommendation to a human who judges whether that recommendation is correct and then provides it to the end user, right? There is a screening that's done. So these are also called decision support systems. These are not decision-making systems unlike Amazon recommendation, right? There's an extreme case of something like a self-driving car where both need to be high, right? That's why those cars are not still on the road. It's very difficult, right? If you make an error, people die, At the same time, so a lot of decisions also need to be made. You can't make an error. Another practical, very practical concern is the data on which you trained might become obsolete. So you trained, take the fraud example. You trained on people doing fraud, right? That was the data you had. Characteristics, fraud or not, fraud or not. People have changed after 1 year. They no longer do fraud in the same way. That model is no longer relevant, right? What do you do then? There are several ways to, so that can happen because of various reasons, right? Underlying processes, that fundamentally underlying processes, which is people that generate the data, has changed. Data capture systems have changed, right? Or the data that is being captured, the structure in which it is being captured has changed because some application has changed somewhere, right? Because this data is typically captured via various systems. 3 things to do there: detect the data drift or change in the data sets, the fact that your model is no longer relevant. It can be done by observing the data itself or looking for degradation of model performance over time, right? Retrain the model using new data. And thirdly, if you don't want disaster, have fallback systems in place, right? Which might not be as good as your machine learning model, but which makes sense and can provide a decent enough result without, so there are 2 things here. One is, if you have a sophisticated system, the complexity also means that it can degrade quickly. Robustness and sophistication sort of are anti-parallel, right? So the more robust your system, it might be simpler. The more sophisticated system, it might be fragile, right? So have a more robust fallback system in place that can take over when the sophisticated fragile system breaks down. Right? Just wanted to go to the 3rd section. There are 2 ways in which connections are being built. One is machine learning being applied to various fields, and the second is the ideas from various fields coming into machine learning, right? So biology, especially genomics, has been like sort of one of the pioneers of actually doing data science and machine learning, right? Like several of the folks who have developed algorithms are people who have worked on genomics. Right? A lot of algorithms have been developed by those folks. So biology is a natural candidate. Another instance where machine learning is being applied is social sciences, where I'll give you a nice example. Some research group recently found out that they looked at Instagram photo data, and found out that Instagram allows you to put filters on photos that you take, right? You can take a photo and put a particular filter and then publish it online, right? They found out that certain kinds of filters were often used by people, correlated with people who have suicidal tendencies, right? Yeah, this is a study that was published. Now, this is a study, the scale at which this study was done would not have been possible without Instagram or without the algorithms that we have, right?
So can't we make, let's say in the case of the retina problems, right?
Yes.
So can't we make a probabilistic prediction that you are in this classification, but our algorithm is predicting 90% then?
You can.
So it's like 60% then you
almost all algorithms only predict probabilities, but ultimately what you're interested in are classes, because people take decisions based on classes, not on probabilities. So you can say, I mean, I'll predict probabilities, but then you'll have to make a choice saying, if the probability is greater than 60, I'm going to act on it. That automatically makes it a class.
Games like the chess, it should be accurate 100%, right? That's only when you can defeat one, right? I mean, this can't be 60% or something.
Sure, agreed. But then, I mean, not 100%, but I mean, what does 100% even mean there, right?
I mean, not even humans are 100% correct.
Like, I mean, see, error also depends on the training set, test set that you're looking at. On one particular test set, it produced a whatever, like it identified everything exactly correctly. Does not mean that when you give a new test set, it will, right? The only thing you could say is that since it has performed well here, it might perform well there, because you can say that it has learned to generalize. That's it. I have 2 more slides. If we have time, we can go through that.
How long will it take?
3 minutes. 3 minutes, that's it. Not thank you, before that. Yeah. So, 2 interesting directions that have emerged, right? So, I briefly mentioned this, enriching the theoretical underpinnings of machine learning. That's another research direction that's becoming very prominent, right? So especially, so in enriching the field itself, in physics what is happening is that people are studying phase transition by doing simulations and try to identify phases as classes using machine learning, right? So I'm not sure whether they are doing clustering or classification, but they are trying to apply machine learning there. That's one of the things that's happening. And the other thing that I wanted to talk about is the theoretical underpinnings of machine learning itself. Deep learning so far has been a sort of a black box, right? In 2015, one interesting paper came out which used a very old principle. They called it information bottleneck principle, sort of to explain how deep neural networks work. Right? Deep neural networks is what is behind the music generation and retina detection and your various applications that you're finding, right? Like Facebook photo recognition or whatever. So the key idea in that discussion, that paper, about that explain how neural networks works, the two key results I walk you through that. The first assumption was this, that if you have a network like this, right, you can take any layer and say that the thing that comes before the layer is my encoder, which is encoding stuff into here, and this is my decoder, right? And you can think of it as a transformation that's happening from the input to the output, right? And you can think of each layer as doing a further set of transformations. What they did is this, they trained a neural network, a deep neural network, starting with layers 1, 2, 3, 4, okay? And they looked at the mutual information between the layers output and the input, and the layers output and the output, right? Actual output, not predicted output. So y-axis has gone off here, but this is just mutual information between T, which is an intermediate layer, and output, which is y. Okay. Now the first layer, so because the input is x is supposedly correlated with y, right? The mutual information should be high, and the first layer sort of knows that, so it is at a high for both. But the other layers are sort of low. As the training progresses, this point starts moving. Each of these layers ka mutual information starts moving up and moving right, which means that it is learning to, the T output is becoming more and more correlated with X, or the mutual information is increasing because it's moving right. At the same time, it's also learning about Y, which is the output, right? True output. That happens until here, which they call the learning phase, and this phase is what they call the compression phase, right? Over here, the mutual information between X and T, or the layers output and the input, actually is reducing, which means that it's becoming uncorrelated with the input. Which means that, but at the same time, what people find is that your test error is decreasing, right? Which means that it's actually compressing from here to here, right? So the information bottleneck idea is this, that you can, the whole, yeah, go ahead.
I'm sorry, can you just tell me how exactly the mutual information is calculated after
Yes, I have not worked it out, but I'll tell you what I understand, right? So what from what I read, what they're doing is this, they are, the input is in discrete, the input is discrete, the output is of each layer is a sigmoid function which they are binning to make it discrete, and they are calculating, they are looking at the joint probability distribution and then calculating mutual information.
Some form of cross correlation.
Yes. Not cross correlation, what they are creating the joint probability distribution and calculating mutual information using that probability distribution.
It's literally the mutual information.
Yeah, it is literally the mutual information, not cross correlation.
SA plus SB minus SA.
Yeah.
Okay.
So, what is interesting is this, right? When a neural network is trained using what is called the stochastic gradient descent, or SGD as I've written here, that's the typical process used to train it, right? That is just a gradient descent. Everybody knows gradient descent, right? You go towards the minima, right? And that's done with some amount of noise, which is called stochastic gradient descent. So using that, when a neural network is trained using that procedure, what they identify is there are two phases to the training. One is when you learn the input features well, and the next is when you compress your representation so that you become less and less correlated with the input features, at the same time retaining the information, relevant information to predict y, which is output. Right? We talked about autoencoders, right? And how it, or dimensionality reduction. You can think of this process as dimensionality reduction that's happening there. So that's that. So that idea is comes from an old paper, 1996 paper or something about informational bottleneck that's been applied now, and it's an interesting result. It's one of the first results that tells us like what is actually happening. How do neural networks actually learn? What are they doing when they're learning, right? And because you have these whatever 100 layers and whatever 5,000 neurons, and you don't know what is really happening. You are just observing the test error and the training error. Okay, any questions? Yeah.
In the other thing, we have this overfitting problem. So here, there's if you train it long enough.
Yes. So any training that you want to do, typically you'll have to look at something like this. You have to look at the test error and training error curve, right? Your test error will start to increase after a point when you start overfitting. So you have to stop here, you're training here. It should not go beyond this. Because then the model is learning to memorize, not generalize.
This one is not related to the
No. So this thing was observed during the training process, that there are two distinct behavior regions in the training. That's it. Okay. The second is by a physicist, Pankaj Mehta at Boston University, I think. And this came out in 2014-15. It was a connection between RG and renormalization group and one particular kind of deep neural network, which is created by using something called Boltzmann machines, right? The key results were this, that they got an exact map between how the deep neural network, it's called a deep belief network in this case, that particular neural network, how that learns. They got an exact map of the learning process of that with the RG process, right? It's an exact one-to-one map. That was fantastic. Couple of caveats there. This RBM, or restricted Boltzmann machine, is defined using an energy functional that is very similar to the Ising model kinds, right? So it was not surprising that it was possible. In general, any machine learning algorithm cannot be expressed using such energy functions, right? So that was one thing, and the second thing is more generic than that, right? So it's a very, this is my last slide, I'll probably take like half a minute. It's a very sort of a nice teasing idea, right? That, hey, when I'm actually learning something, like imagine the red, blue, green stuff, the first slide, right? I'm actually learning that this is red, this is blue, this is green. What is red but just a coarse-grained description of all the data that is there, the label red. So it's a very like a nagging teasing thing that, hey, there is an element of coarse graining in learning, right? But then how do you actually reconcile with other coarse graining mechanisms that you know? Right? So it's a very interesting idea and a very interesting direction that needs to be further explored. Keeping in mind that supervised learning, for example, is learning the coarse grained description. It's not generating the coarse grained description. Whereas something like RG is actually coarse graining the microscopic degrees of freedom and coming up with a coarse grained description, right? So the end goals of both are slightly different. Machine learning is about learning coarse grained descriptions. RG is about creating coarse grained descriptions from finite details, right? So they're not exactly the same, the end goals or the lens through which you look at coarse graining, but there is an interesting connection there. I think that was my last slide. Thank you.
Maybe questions? Yes. There are a lot of questions. We have questions in the key session looks like. Let's try for a second.
Thank you.